Hi guys, so here we'll start out with section 3 with bond energy. So you'll need your notes, which is your pen and paper. So let's take a look at this reaction. We have CH4 plus O2 produces CO2 and H2O. We've seen this reaction a ton of times. Let's go ahead and balance it. When we do, we find out that we need 2 oxygens and 2 waters for every 1 methane and 1 carbon dioxide. What we have down below is showing you particles, so pretty much how they're arranged. So I'm going to draw a line between the reactants and the products. So here in methane, we see that we have a central carbon and 4 hydrogens attached to it. For the oxygen, we have 2 oxygens bound together because these are diatomic molecules, and then we have a total of 2 diatomic molecules attached to one another. So when we talk about the specific atoms, we have 4 specific atoms of oxygen, and each of them have a double bond with one another. On the right-hand side, we form a carbon with 2 oxygens, each of which have double bonds, and then of course with water we have our oxygens and hydrogens attached to them. So when we're looking at this, we have 4 bonds between a carbon and a hydrogen on the left-hand side, 2 double bonds between the oxygens. On the right-hand side, we're forming a double bond between the carbon and the oxygen, in fact 2 of them, and 4 bonds between oxygen and hydrogen. So we know that we need energy in order to break bonds. So energy must be absorbed when breaking bonds. It's an endothermic process. So what we'll take a look at is to figure out how much energy is in fact needed. So let's, in order to do that, you have to figure out first how many bonds are being broken or formed. So with this methane, we're breaking 1, 2, 3, 4 carbon-hydrogen bonds. So 4 carbon-hydrogen bonds. And with the oxygen, we're breaking 1, 2 oxygen bonds. In fact, we'll end up adding those together and seeing how much that compares to, if it's greater than, equal to, or less than the energy for the products. So if we take a look on the product side, we end up forming 2 carbon-oxygen bonds. In fact, they're both double bonds. So 2 carbon double-bonded oxygen. And since we're forming those bonds, energy is being released. When we release energy, we show that it's a negative sign. So we'll say it's a negative value for that. And we'll add that to take the sum of how many hydrogen-oxygen bonds were being broken. So 1, 2, 3, 4, being formed. 4 OH bonds are being formed. Again, since this is an exothermic process, we'll go ahead and subtract them. So we want to figure out how much energy it takes for the reactants versus the products, and again figure out if it's greater than, equal to, or less than, or how they compare with one another. So let's put some values in here. We scientists know that we have specific values for each carbon-hydrogen bond. So in fact, it takes 413 kilojoules to break a hydrogen, to break a bond between carbon and hydrogen. So again, 413 kilojoules, not something you need to memorize, it's something that we would look up on a table. And since there's 4 of them, 1, 2, 3, 4, we multiply that value by 4. So here's what we have, that 4 times 413 kilojoules, and the 413 kilojoules were for each carbon-hydrogen bond. We'll add that to the other reactant, which is oxygen. It takes 495 kilojoules to break a double-bonded oxygen. So if you notice, it takes a lot more energy to break a double bond here than a single bond. And there's 1, 2 of those together. When we add those up, we end up with 2,642 kilojoules of energy needed in order to break the bonds of the reactants. Once those bonds are broken, we have to form or reform different combinations. So when we do that, energy is being released when we form those bonds. So this is an exothermic reaction. We know that we'll make those signs negative. So we can look up on a table, or scientists know that between every carbon double bond to an oxygen, it releases 799 kilojoules of energy. So there's 1, 2 of them. That's this part right here. So it's every carbon double bonded oxygen. We're making it negative because energy is being released. That's where that negative sign is coming in right there. For the other product, water, we're forming, let's say, a bond between oxygen and hydrogen. And for each one of those, that's 467 kilojoules of energy being released, or negative 467 kilojoules. We have 1, 2, 3, and 4 of those being formed right there. So we'll show that the oxygen bond to the hydrogen is 4 times negative 467 kilojoules. So really it takes negative 3,466 kilojoules in order to make the products, in order to make the CO2 and the two waters. So we'll compare that to how much we had when we made these. So let's go back to the last screen. It was 2,642 kilojoules, so 2,000, oops, let's go back, 2,642 kilojoules in order to make, or excuse me, in order to break the bonds, and it released 3,466 kilojoules. Just to make it easier on yourself, if you just want to look at the absolute value, that's fine of it. But really, there's more energy in the products. Since there's more energy in the products, in order to make these bonds, it ends up being an exothermic reaction, and I'll show you why in just a bit. So here we have two graphs. We'll focus on the one on the left-hand side first. This is an exothermic reaction. So in order to break those bonds, it took 2,642 kilojoules to break those bonds. Here it took, what, negative, let's see, it took 3,466 kilojoules. Oopsies. There we go. Kilojoules in order to make them. So I think that was the value, kiddos. I forget. That's about right, though. So the energy of the reactants must equal the energy of the product. So what happens to all of that energy? Well, all of that energy ends up being released out by the products. So it feels warmer, you feel heat from this, or you might see light from this, or a flame might form. So again, this is for an exothermic reaction. For an endothermic reaction, the amount of energy it takes to break the bonds is going to be greater than the amount of energy produced from forming those bonds. So, in fact, the reactants will have more energy than the products, so that's why this ends up being an endothermic reaction. So to let you know, these net changes, those are what your delta H's are. So your delta H is really the energy of the products minus the energy of the reactants. And to make it a little bit more formal, we actually also say it's the sum, that's the sum symbol, of each mole of the products minus the sum of each mole of the reactants. Again, this is the energy needed. So essentially this is your H value. Oops. How much energy is needed for that. So that's what your delta H really means. So here we show that since energy is being released, this is a negative delta H. So if you take the amount of energy from your products minus the reactants, it ends up being negative. Here on the endothermic side, this ends up being a positive value. All right, so let's take a look at some trends. The smaller the atom, the stronger the bond. So if we take a look at hydrogen, let's go ahead and draw the nucleus. We have one proton in there. We're going to focus more on the protons because that's what's going to do all the attraction, and one electron. So again, this is a hydrogen. We'll draw another hydrogen. So one proton in there, and we'll show the other electron. So really, there's an attraction between this nucleus and that electron. Same thing with this nucleus and that electron. So that ends up being a pretty strong bond, versus if you had something like chlorine. Here's the nucleus. And let's see, let's draw the shells. Since there's more shells in there, there's a greater distance between this nucleus of one chlorine to the outer electron of another chlorine. All right? So the smaller the atom, the stronger the bond. Also, triple bonds are stronger than double bonds, which are stronger than single bonds. So if you had a carbon single bonded carbon versus a carbon double bonded carbon versus a carbon triple bonded carbon, this one has the most energy, the one that has the triple bond. All right, to summarize, we know energy is absorbed by breaking bonds, so we need to put in energy to break bonds, and energy is released by forming those bonds. An exothermic reaction is when energy formed by the products is greater than the energy released by the reactants. And endothermic is the opposite. The energy from the products is less than the energy released by the reactants. So let me know if you guys have any questions. Have a good day.